Welcome to our webinar, Maximizing Efficiency, Writing Power Efficient Code for Embedded Systems. I'm Mark Thomas, Security Field Application Engineer at IR, and I'm here to introduce Raphael Taubinger, our Product Marketing Manager. Raphael will explain key techniques for writing power efficient code in embedded systems. He'll go over strategies to help reduce power consumption in both battery-powered and energy-constrained devices. This session will provide useful insights to help you create more efficient embedded solutions. Let's begin. The stage is all yours, Raphael.
So let me dig into details about writing power efficient code for embedded systems. Power efficient code has been relevant for a long time, mostly because of battery lifetime, like a pacemaker, for example. But nowadays, it's about sustainability and the cost of operations. Think about the 15 billion or more IoT devices. I guess nowadays we are already forecasting double of it for 2030. So if each device here can save maybe 5% of energy, what is the cumulative energy here for a year, for the lifetime of the device? Well, you can do the math. So what can we do for optimizing embedded software for energy efficiency? So for the next 30 minutes, I will cover the following agenda. So I will first start talking about performance and low power, or maybe better, performance versus low power. And then I move into the optimization of code. Moving on, I will then talk about minimizing and optimizing power. And to finalize, I will present a practical example. And at the end, we will have a summary. So performance and low power. That's of course a good question because we want from one side to make sure that the performance of our application still stays on a good enough level or maybe the best. But on the same time, when you think about low power, it almost correlates to having your application maybe running slowly or not having that kind of response you would expect. But of course, to get this balance, you need to have the right tools. And to minimize the power, then you need to optimize your application correctly. And then, of course, keep measuring the power and correlate it with the source code. It's not about just guessing. You need to know exactly which parts of your application maybe tend to consume more or generate some peaks. And then you can definitely work on these areas first because that's like the low-hanging fruit to make sure to optimize your application best. Optimizations. Well, that's very important too because you should trust the tools you are using. You should trust the compiler you have. So when you think about what options do we generally have when thinking about optimizations in your application that the compiler can do, first we have size optimizations. You might need more room for new features, you want to use a cheaper device, and of course use a device with less memory because memory is what of course costs mostly. On the other hand, you have speed optimizations. That's of course for a better response time, faster execution. And now we are talking about power. So how does that fit? The tools, they can generate code for optimized size or optimized speed, but we are thinking about power here. And as we will see here, power, of course, to saving power and enhance battery time, it's all related to use speed optimizations. You mainly do as fast as what you need, and then the rest of the time you spend on sleep or idle. And very important, it's not all or nothing. There are, of course, different levels of optimizations that you can make use. You can, of course, optimize the entire project for size or for speed, but that's not the best way to solve this because you have your application set up in different ways. You have your application, you have the libraries, You have some routines that need to run faster, so what you can mainly do is to make sure that you use the right optimizations for the right part of your application or source code. I mean, you can define it for groups of files, for a file, or even a function. What I'm trying to say here is that when you're working with embedded projects, you have definitely these BSP or Hall drivers that are being provided by the silicon vendors, and that's of course the files that you should optimize for size. It's a lot of code, but your own application that needs to be reactive and fast, that you can optimize for speed. But on the same level, you can choose a specific file or even a specific function. You maybe place that function even in RAM and optimize it for speed. So that will run as fast as possible, and then later you can do some further adjustments. So let's dig in minimizing power. So what do we need to do to minimizing power consumption? So as mentioned before, we need to work fast and sleep a lot. So that means writing efficient code. Well, when I say efficient code, that means to make the right use. More will come here on a bit later on these slides. And as mentioned before, use the right compiler optimizations. But very important, you need to measure how your application behaves on the target. So what you can do is use some power debugging techniques. It's mainly to tune your application to minimize the power consumption when it uses the hardware resources. So of course this needs to be enabled by some probes like iJet or other hardware with power debugging support. I mean, there are plenty of examples out there. You can use the solutions from ST, you can use the solutions from Sager, J-Link, but even some TI probes support that. So you need to make sure that you can really measure how your application is behaving, and then you can focus on which areas you can optimize here. So power debugging, I introduced this concept. What does that mean? So power debugging is this methodology that provides developers with information about how the software implementation in the embedded system affects the power consumption. So by coupling source code to power consumption, testing, and tuning, you will enable the power optimizations. As mentioned before, battery lifetime is a very important factor for many embedded systems in almost any segment. But nowadays, this is also very relevant for home automation and more. So power consumption has traditionally been a design goal for hardware developers. But however, nowadays, the power consumption depends not only on the design of the hardware, but how it is used, meaning how it is controlled by the system software. So how does power debugging work? The technology of power debugging is based on the ability to sample the power consumption and correlate each sample with the program instruction sequence and with the source code at the end. One of the difficulties is actually to achieve high precision with sampling. The best would be, of course, to sample the power consumption with the same frequency as the system clock. But of course, how hardware is implemented reduces actually these capabilities for such measurements. So how is that achieved in practice? So from the software developer's perspective, it's more interesting to correlate the power consumption with the source code and various events in the program. So how is that achieved? So power is measured by the debug probe, like iJet, for example. So it mainly measures the voltage drop across a small resistor in series with the supply power to the device. In the figure here, we can see the voltage drop that it's measured by a differential amplifier and then sampled by an AD converter. In order to make this work in a good way, I can mention here the ARM CoreSight debug module on Cortex-M. So the key to accurate power debugging is a good correlation between the instruction trace and the power samples. So the best correlation can be done with a complete instruction trace if available, like with ARM ETM support. Of course, ETM requires a special probe and not all devices support it. Maybe a bit less accurate, but still giving good correlation is the chance to use PC sampling that's available on Cortex-M devices like M4, M7, and so on. The picture mainly shows all these capabilities that can be used. So as you can see, there are plenty of features here, from watch points to PC sampler. You can also have the time sampling, but you need to have the JTAG or SWD, SWO interface available to make these measurements work. So what can we do when we have this all in place? I mean, a debug probe, we use a device that can provide information about samples with PC sampling and time sampling. So that brings us to the ways that we can plot or display this information. The first one that I want to discuss is power debugging, the power log. So, of course, power debugging is based on the ability to show this information. So here is an example that we use a power log window that can log all the collected power samples. This can, of course, be very useful to find peaks in the power sampling and, of course, with the correlated executed code. From the power log, you can get to the corresponding code, of course. And depending on the power sampling frequency, the precision will be different, but of course, there is a good chance that you will find the code sequence that caused that peak, for example. Next one, it's the power debugging timeline. So this is, of course, the best way of visualizing what's going on in your application. It's, of course, graphically. So in the timeline, the power samples are then displayed in a time scale together with other activities like interrupts and even variables that you can select. In embedded systems, peripheral devices often account for much of the power consumption, and how software controls these peripherals is actually how it will reflect on the power consumption. So this view, of course, provides a very convenient way of visualizing the power consumption in relation of both function calls, variables, interrupts, and the peripheral use and so on. Of course, the goal here is to give you the visibility in the timeline on which parts of the application you can try to optimize the power usage. Again, the timeline is, of course, also related with the power log that I mentioned before. And from here, you should easily be able to navigate through the source code because all it's related here, and we have the information about the program counter in all the steps. Next capability here is, of course, the power profiling. This is, of course, a very useful feature, and mostly we are interested in to have in practice a task-oriented system, and we want to know how a particular function affects the consumption in general. So the function profiler will, of course, help you to identify which parts of the application you're spending most time, and this is, of course, the areas where you should invest efforts first. So it will show you which parts of the application you're spending most of the time, but on the same time, it will also show you how much energy you are spending in this function. So by choosing the highest ones first, you can get the best or the quickest effects out of it for optimizing your application. And in a practical way, the function profiler will list, of course, the number of samples per function and also the average values together with the max and minimum values. This is a very convenient way, again, as I mentioned before, to finding the peaks and some abnormal behavior when it comes to power consumption. As always, the system can appear to be fully functional and behave as expected, but the power consumption might not be optimized yet if you don't look into the detail. So optimizing power. So let's discuss some of the approaches or implementations you can do directly in your source code to optimize the power consumption. One common mistake that could cause unnecessary power to be consumed is the use of a pull loop to wait for a status to change, or for example on a peripheral device. Code constructions like displayed here execute without interruption until the status changes. So it's just waiting the status to change. Another construction that could be using a lot of power without you really taking that in consideration, it's a software delay, like shown here with a while loop. So this piece of code keeps the CPU very busy executing instructions that don't do anything else as passing time. And yes, in tough situations, the code could be changed to minimize the power consumption. Time delays are much better implemented by using hardware timers. The timer interrupt can be set up, and after the CPU goes down into a low power mode, it's awaiting again by the interrupt. Also, just pulling a device status change could be something that could be a small improvement here by using interrupts. So, well, when it comes to the key rules to saving power, so just get it in the way that as soon as you have some time to spare, just take a nap. If you're using an RTOS, that's usually already handled in best ways because there are always some low priority tasks that can help you to solve that in an easy way. DMA versus pooled I/O. So DMA has traditionally been used to increase transfer speed, but in the MCU world, chip vendors have invented lots of different DMA techniques to increase flexibility, speed, and of course lower power consumption. In some architectures, the CPU can even be put into sleep mode during the DMA transfer. So power debugging allows the developer to experiment and then see directly in the debugger what effects you can get from these different DMA techniques, and of course compared to the traditional CPU-driven pooled approach. Low power mode diagnostics. So many embedded applications spend most of their time waiting for something to happen, receiving data on a serial port, watching an I/O pin change state, or waiting for a time delay to expire. If the processor is still running at full speed when it is in idle, so battery life is being consumed, while very little is being accomplished. So in many applications, the MCU is only active during a very small amount of time, and by placing it in low power mode during the idle time, the battery then can be of course extended and you can save a lot of power. A good approach is of course to have a task-oriented design and to use an RTOS. In a task-oriented design, a task can be defined with the lowest priority and it will only run when there is no other task that needs to be run. This idle task is then perfect to place the implemented low power management. In practice, every time the idle task is activated, it puts the processor into low power mode. And of course, many MCUs, they have a lot of different low power modes. So in these low power modes, of course, it can turn off certain parts. So next one, CPU frequency. So power consumption in the MCU is theoretically given by the formula, where F is the clock frequency, U is the power supply voltage, and K is a constant. So power debugging allows developers to verify the power consumption as a factor of the clock frequency. A system that spends very little time in sleep at 50 MHz is expected to spend 50% of the time in sleep mode when running at 100 MHz. The power data in the debugger will allow the developer to verify expected behaviors and if some unlinear dependency of the clock exists to choose the operating frequency that gives the lowest power consumption. Again, here it's a matter of measuring, and of course if you use the compiler optimizations to generate faster code, you might already have the chance to use a bit lower frequency and have the same performance or results. But it's always best to measure because each application might be a bit different. So interrupt handling. So let's take an example involving interrupts to illustrate a good situation where it's difficult to identify how a system consumes unnecessary energy. In this specific case, the figure shows a schematic diagram of the power consumption of an event-driven system, where the system at T0 is an inactive mode and the current is at I0. At T1, the system is activated, where the current rises to I1, which in the system power consumption in active mode with one used mode peripheral device. At T2, the execution becomes suspended by an interrupt, which is handled with higher priority. Peripheral devices that were already active are not turned off, although the thread with higher priority is not using them. Instead, more peripheral devices are activated by the new thread, resulting in an increase in the current I2 between T2 and T3, where the control is handed back to the thread with lower priority. So the functionality of the system could be excellent, and it can be optimized in terms of execution speed and code size, but in the power domain, more optimizations can be done. The yellow area represents the energy that could have been saved if the peripherals that are not used between T2 and T3 have been turned off, or if the priorities of the two threads could have been changed. Using power debugging would have made it easier to discover this increase of power tune. Finding conflicting hardware setup. To avoid floating inputs, it is a common design practice to tie unused MCU I/O pins to the ground. If the software by mistake configures one of the grounded I/O pins as a logical 1 output, a current as high as 25 mA may be drained at that pin. This high unexpected current is easily observed by reading the current value from the power graph. It's also possible to find the corresponding erratic initialization code by looking at the power graph at application startup. A similar situation will arise if an I/O pin is designed to be an input and is driven by an external circuit, but the software incorrectly configures the input pin as output. Turn off your peripherals. Of course, this is very trivial, but the problem is that peripheral units in an embedded system could consume a lot of power even if they are not actively in use. If you are designing for low power, it is very important that you disable them and not just leave them unattended when they are not in use. But for different reasons, a peripheral can be left with its power supply on. So it's important to make sure that you can measure and see the effect when the peripheral is really turned off. In some cases, just disabling the clock, it's not enough. So the timeline window with the corresponding source code will allow you to find the cause of problems when you modify your application. And when you disable the peripherals, you can see that directly correlated in the total consumption of your application. So talking about memory accesses. A very costly operation in terms of power consumption in embedded system is accessing memory. If you can optimize memory access, then we will save power. There are two general principles for doing this. The first principle is to minimize the total number of memory accesses. The second is to do the ones you need as close as possible from the CPU. Every system has a memory hierarchy, and the further away from the core the memory is, the more it is expensive to access it. So in a microcontroller, of course, registers, RAM, and flash are available. So it is the best approach to keep data in registers, but if registers are not enough, then they might be located in RAM and later in flash. So if you manage to move items from flash to RAM, that's of course a good step. And once you have put critical function into RAM, then you can look on how you handle the data that is stored in memory. So when a variable or a constant is in the program, it's read into a register. While registers are of course the fastest way, they are limited. It's probably a good practice if you try to group the accesses, and there's also a chance to use some specific pragmas to force some variables to be placed in registers. Global variables are not maybe considered the best practice, but still very frequent in use. So if you access a specific variable more than once in a function, then it's probably a good idea to make a local copy and manipulate that and put it back later once you are done. So if you can, of course, group function calls together, that makes it also easy and cheaper when accessing memory. So analog interference. Of course, mixing analog and digital circuits, it's already a challenge. But power debugging can also help you when investigating some interference when it comes to power supply and so on. So you should probably avoid toggling some I/O or a lot of I/O activities while you're sampling some analog signals or reading some information. But again, this can be some good insight on what's going on your circuit. So now over to Michael that will show us a practical example.
I will be using the IR Embedded Workbench for ARM for my demo, together with a standard iJet debug probe and an evaluation board that is based on an STM32F4 device. I have here the CoreMark benchmark as a small example project, and if I open the compiler optimization settings, then you can see the application is being optimized with high optimization for a small code size. So let's build the project and start a debug session. I have to enable the terminal I/O window because the benchmark is printing out some messages via printf. And then I want to show you the function profiler, which I need to enable. And if I right click into the window, then you can see that I have the option also to include the sampled values from the power measurement. So let's start the benchmark. And if I click on the PC count label here, then the entries will be sorted and you can see that there is a live update. And here you can get the percentage of execution time that each function is active. And here on the right hand side, it's the percentage of the total energy consumption that this function is contributing to. Then at the end, here it's also the min, max and average values for the power consumption. So the minimum value was 53 milliampere, the maximum value is 60 or 61 for this function, and with an average of around 56 milliampere. With the high optimization for small code size, I receive a CoreMark result of around 2.1 CoreMark per megahertz, and let's assume that this is the required performance for my application. So if I want to reduce the power consumption of the application, I would have two options: increase the performance and then put the controller for some time into sleep mode, or increase the performance and reduce the clock frequency of the MCU. So if I want to, or if I need to increase the performance, it's a good approach to start with the function that is executed most of the time. So I can simply double click on this core state transition here, and then I can enter a pragma statement. Pragma optimize no size constraints, and this tells the compiler to use high optimization for the fastest possible execution time for the next following function. So let's rebuild the project and start a new debug session. So if I run the benchmark again, you can now see that the CoreMark value increased from around 2.1 to 2.4, which is a clear improvement. And then the next step could be to also add this pragma for the second most executed function in the list, and to continue step by step until you have reached the maximum value of the flash consumption that is still okay for your application. And then you could use this increased performance either by to set the MCU into sleep for a certain amount of time to check how long this sleep period can be until you still have the required performance and what is the effect on the power consumption. Or you could give it a try to reduce the clock frequency of the MCU. So it's a step-by-step approach to find the sweet spot between flash usage, performance that can be reached by the application, and the power consumption. So with the tools you would have everything in place to get an overview how the optimization, or at what areas the optimization makes sense, and what is the impact on the power consumption to get the, let's say, smallest possible code size, the required performance, and the lowest possible power consumption. So let's stop the debug session and switch to the FreeRTOS project. And here I want to start with opening the project options, going to the debugger category, and here on the right hand side you have the tab for the plugins. So here it's the list of available debugger plugins, and after the example project is using FreeRTOS, I'm enabling the FreeRTOS with task global context, and the second plugin FreeRTOS and OpenRTOS. So these two can be used to give you additional information of a FreeRTOS application that is running. So let's build the project and start a debug session. And what I need here is, let's open the task window. I want to use the timeline. And here I need to enable the interrupts display, the power measurement, as well as the ITM events. And then I want to enable the power log as well as the power log setup window. So let's rearrange the windows a little bit so that it's enough space on my screen. Of course, I need to enable my power log as well. And then let's start the application and run it for a second. And here on the lower end of the screen in the task window, you can see that this FreeRTOS is using 4 different tasks: an idle task, a task that is responsible for sampling of the ADC, then one that is sampling the buttons on my board, and the default task. You can see the individual task numbers and the state that the tasks are in when I halted the execution right now. Then let's proceed to the power log window. Here you can see on the left hand side the timestamp when the power values were taken, the corresponding address of the program counter, and the measured power values. So for example, if I want to check what happened when my application consumed these 20.8 milliampere, I can simply double click on the program counter, and then the source browser and the disassembly will jump to the corresponding address. So this can be quite helpful if you see, for example, a peak in the measured values and you want to know what happened when this peak was sampled. I can right click into the window and then I could say save the collected data to a file, and then I could use, for example, Microsoft Excel for further analysis. So let's run the application for another few seconds and then let's zoom out. And you can see that when the application is running, there are some peaks in the power consumption. So let's look into the details of one of these peaks. So let's pick that one here and zoom in. And in the interrupts display here of the timeline, you can see, for example, that the ADC interrupt was triggered, which means that this peak in the power consumption was caused by the ADC, that it was reading a value in the background. And if I open a file here, tracefun.c, you can see that the ITM event channel number 2 is used to send out the task number from my RTOS. So I can also have a look at the data here at ITM2. And if I zoom in even further, for example, here I can see it was after the ADC sampling was done. It was task number 1 that got active again, which means after the sampling was done, the application was switching back to the default task. So you can use this available information to get a detailed inside overview what happens inside your RTOS, and you can also see the relation between the interrupts that are happening and, for example, some peaks in the power consumption that might be triggered by some functionality that got triggered inside the interrupt service routine. So let's continue the application for a short moment. I'm pressing a button, and you can see that when I press the button, additional rows in the interrupt view popped up. So if I zoom out, then you can see here I pressed a button on the board that started the audio output. And this audio output is done by a DMA in the background, and then with the second press of the button, the audio was switched off again. So let's do this again and turn the potty to increase the volume so you can see, hear the speaker. And I can also see then in my power consumption that the audio output created some peaks because it's a sine wave that is sent to the speaker, and then you have sort of sine wave shape here also in the power consumption when the speaker is or when the MCU or the DAC is driving the speaker. The last thing that I want to show you is here in the power log setup window, you can set a power breakpoint. So for example, I could tell the application to stop if a value of 100 milliampere is exceeded. So log all the values and halt the CPU if the threshold is being exceeded. So if I run the application now, switch on the audio output and increase the potty value, you can see that the application was halted, and unfortunately the audio output is running in the background via the DMA, which means you can still hear the noise, and I have to reset the controller in order to switch off the speaker. But you have seen that you can use this power breakpoint here to trigger or to stop the application once certain values have been exceeded.
Great. To summarize this session, so the power debugging methodologies explored in the sessions can give you, as a developer, the opportunity to examine the application program and correlate it to the power consumption. With this information, you can then synchronize and optimize the source code in order to minimize the energy requirements. And we want to ensure that your project can be as energy efficient as possible, of course without compromising the performance of the application. Great! Thank you so much.